In the previous lecture, we had a look at Hartley's definition for the measure of information. This definition was based on two assumptions. First assumption was that each symbols which built up a message can take any value from q possibilities, but all these q possibilities were equiprobable. That was the first assumption which went into the definition of Hartley's measure for information. The second assumption was that all the symbols which built up the message are independent. Today we will have a look at the definition as provided by Shannon. This definition of information is more generic and it overrides the deficiencies of Hartley's definition for information. To arrive at the definition provided by Shannon, let us approach this definition from the understanding of common sense. Let us take a simple example. Suppose if I were to read the following three headlines in a morning newspaper. The first headline says, tomorrow the sun will rise in the east. The second headline says, India wins the cricket match series against Australia by 5-0, and the third headline says there is snowfall in Mumbai. Now, if I look at all these three headlines, then based on my common sense understanding of the word information, I can say that the first headline provides the least information, whereas the third headline provides the maximum information. Let us look at the probability of occurrence of the events associated with each of these headlines. The probability of occurrence of the event associated with the headline number 1 is almost 1, it is almost certain, correct? Whereas the probability of occurrence associated with the event number 3, which says that there is a snowfall in Mumbai, is almost 0, it is not very certain. So, what it means that if the probability of occurrence of the event is lower, then there is a higher surprise and therefore there is more information. What it implies that information is connected with an element of surprise, which is a result of uncertainty or unexpectedness of the occurrence of the event. the more the unexpectedness or uncertainty of an event, higher is the surprise and more is the information. The probability of occurrence of an event is a measure of uncertainty or unexpectedness of that event. So, based on this discussions, the common sense understanding of an information measure would be that information is directly related to uncertainty or inversely related to the probability of occurrence of that event. So, what we should do, that when we define the information measure, we should define in a manner which takes into consideration this common sense understanding. For example, if the probability of occurrence of an event P tends to 1, which was the case for the statement number 1 or headline number 1, then the information which I should get from that event should tend to 0. Whereas, when the probability of occurrence, like in the case of the statement number 3 or headline number 3, tends to 0, information should tend to infinity. With this understanding of expectations for the measure of information, we will try to define information more formally as defined by Shannon. So, to define information more formally, I would say, let me assume that I have an event E and the probability of occurrence of this event E is given by P E. Then, when the event E occurs, the amount of information which I get on the occurrence of the event E will be defined as I of E is by definition log of 1 by probability of E. I define using this relationship. Let us look into little more depth as far as the definition is concerned. If you look at this definition, it satisfies my criterion number 1 out here, which says that if the probability tends to 1, then information tends to 0, and another requirement is that if probability tends to 0, information tends to infinity. So, this is a reason for choosing the measure which is inversely proportional to 1 by PE. Now, the question that comes to my mind is, why should I choose a function log and why not something other than log? The reason can be explained again based on our common sense understanding of the word information. Let me take a simple example. Suppose if I have an event E, this event E consists of 2 sub-events, let me say E1 and E2. Let me assume that both event E1 and E2 are independent. So, probability of occurrence of E1 is independent from the probability of occurrence of E2. Now, if I were to ask you what is the information which I get when the event E occurs, which consists of 2 sub-events, then I would say by this definition I am supposed to find out information E associated with the event E is nothing but log of 1 by P of this event E. Now, this I can write as log of 1 by probability of event E1 E2. this I can simplify as log of 1 by probability of E1 plus log of 1 by P of E2 based on the assumption that E1 and E2 are independent events. So, what I get is I get E of information from E1 plus information from E2. Now, this kind of additions of information from two sub-events to get the final information in the event E can happen with only log functions. It is not difficult to show this. Therefore, the choice of log function is there for the measure of information. Okay. With this, let us go ahead and let us try to calculate the amount of information for a specific case of say a TV image. Suppose if I have a TV image and using this definition for information, if I ask you to calculate the information which I get when I view one TV image, then this can be done as follows. Let me assume that each TV image consists of 572 lines and each line consists of 720 pixels, that is picture elements. So, one TV image consists of 414,720 pixels. If I presume that each pixel can take values from 0 to 9, that means it is allowed to take only 10 gray levels, then the number of TV images which I can form based on this specification and each gray level consisting of only 10 values, the number of pictures that I can form is 10 raised to 414,720. These are the total number of pictures, TV images which I can form, assuming there are 10 gray levels. If I assume that any of this picture can occur randomly, then the probability of occurrence of any particular image will be given by, let us call that event as E, then the probability associated with that event E would be 10 raised to. And now to calculation of the information for this TV image is straightforward, that will come out to be this comes out to be approximately bits. One thing is important to note, that in my definition of for the information I am assuming that the base out here is 2. It is not necessary for me to restrict my base to 2. I can choose any other base, and it is very easy using the simple conversion formulas between the bases to convert from one base to another base. But as far as this course is concerned, most of the time we will be restricting ourselves to the base 2. So, whenever log is written for the information, it is understood that it is to the base 2. Okay. Fine. So, what I get, the information for one TV image turns out to be 1.4 into 10 raised to 6 bits. We will see later on that is this calculation of information from one image really correct or not. We will find that what we have got, this value is on much higher side, and the information contained in a real TV image would be much less than this. We will look into that little later in our lecture. Okay. So far what we have done is that I have tried to define the information associated with one particular event. Let us take another case. Suppose I have a source S. Let me indicate that source S by S, capital S, and this source S emits symbols Si. It keeps on continuously emitting the symbols. So starting S1, S2, S3 like that, continuously it keeps on emitting. And now the question comes to my mind is it possible for me to associate some kind of measure of information to this source S? How do I associate the measure of information to the source S? We have seen how to associate the measure of information to a particular event. To solve this problem, let us look at the emission of the symbols from the source and put them in the form of a string. So I assume that the first time instant when I get, I call that symbol which is emitted from the source S as S1, then I get S2, and like this. Let me assume that I have n number of symbols which are emitting from this source S. Now each of this symbol which I have got Si, this itself could take any of the q values from the set. So Si belongs to a set S1, S2 and Sq. So these are the only values which Si can take. With each of this S1, S2, Sq, there is a probability of occurrence associated with it. Let me call it as P of S1, P of S2 and P of Sq. Let me make one more assumption for the time being. I assume that all these symbols which are being emitted by the source S, they are independent. The occurrence of a particular symbol in this string, say Si, is not dependent upon the occurrence of the previous symbols. That is the assumption which I make to start with. So if I look at this source now, this source emits the symbol Si. Each of Si can take the values from this set given by this q possibilities, and with each of these q possibilities there is associated probability of occurrence. This specification is, both these specifications are more than sufficient for me to identify this source S. This set is called as source alphabet. And with each alphabet in this set, there is a probability of occurrence of that of that symbol in that alphabet given by this values PS1, PS2 and PSQ. Okay. Now if I am assuming this symbols emission to be independent, then I will call this source S as a zero memory source. So, let us see whether we can assign some kind of a measure of information to a 0 memory source, which is given by the source alphabet and the probability of occurrence of each symbol in that source alphabet. As I have said, let me assume that the string goes from S1 Si up to Sin. N is the length of the string which I get from the source. Let me presume that a particular symbol in the alphabet S1 occurs in this string N1 times, S2 occurs N2 time, and similarly SQ symbol occurs NQ time. With each occurrence of symbol S1, the information associated to that S1 would be I of S1. Similarly, whenever S2 occurs, I can find out what is the information which I get from the occurrence of S2, and similarly for I, S, Q. These are the information which I get when a particular symbol occurs. Now, if S1 occurs N1 time, and if I assume that all the symbols are independent, then the amount of information which I get from N1 symbols S1 would be N1 times I of S1, and similarly I will get for S2 and finally for SQ. So, total information which I get from this string S1 to Sn would be the summation of all this. So, the total information which I would get would be nothing but summation of all these values. Now, if I am interested to find out the average value, I can simply divide this by capital N. If I divide this by capital N, then I can write this expression which I have this out here. Let me just denote it for time being. I will denote it by H of S. I will denote it approximately equal to this. This is the total information. This is the abbreviation which I am going to use for this quantity on the right hand side. Then I can simplify this quantity to HS is nothing but summation of So, going back to the previous expression, N1 by N, N2 by N and NQ by N, if I use the law of large number, then what I get, they are nothing but P of SIs, and this is a summation which I will get. I substitute the value for ISI as log of 1 by PSI, and what value I get is this. So, this is the average amount of information from that source S per symbol. This average amount of information per symbol is for the source S is termed as entropy of S. . 。 . 。 . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now, this entropy of S is dependent on the distribution PSI. Is this entropy of S bounded from the lower side and the upper side? Let us try to look into this. If you look at HS definition, is nothing but PSI log 1 by PSI. PSI values can go from 0 to 1. So, PSI is always positive, log of 1 by PSI is always positive. So, what it implies that each of this term is always positive. So, the summation will be always positive. So, HS always has to be greater than 0, it cannot be negative. That is the first conclusion which we can make about the property of HS. What is the minimum value and what is the maximum value? That question can be answered very easily if we follow this following approach. Let me assume before we try to find out the minimum and the maximum value for HS, let me take a simple function and let me look at the property of that function, because that property is going to be utilized for the derivation of the maximum value for HS. Okay. If I have a function which is given by y is equal to log x, then I can plot this function y log x, and the plot would look something like this. This will be my plot for y is equal to log x, this value will be 1, 2, this is approximately. If I look at the plot of y is equal to x minus y 1 and I draw the same plot on this graph, then what I will get would be something like this. This would be the plot for y is equal to x minus 1. So, graphically I can say that log x is always less than equal to x minus 1, and both the quantities are equal only at 1 and 1 point, and that is x is equal to 1. So, if I just multiply this quantity by minus 1 on both the side, what I will get is log 1 by x is always greater than equal to 1 minus x. So, with this small inequality, we will go ahead and find out what is the maximum information, what is the maximum value which we can get for the entropy of the source, or what is the maximum information contained in a particular source S. Before I go ahead with this derivation, let me try to derive one more inequality which will be used later on. Let us assume that I have two sets of probabilities given by x1, x2 up to xq, and another set of probabilities as y1, y2, yq. These are both two different sets of probability. So, it means xi is always greater than equal to 0 and yj is always greater than equal to 0 for all I and j's. I and j obviously ranging from 1 to q. So, since these are probability, this summation over I 1 to q will be always equal to 1, and this summation out here would be equal to 1. Now, let me just take a simple expression. If I have an expression like this, log I can write this as I just substitute the value for log of y I upon x I. We have seen from this relationship that log x is always less than x minus 1. So, if I use this relationship, I can write this relationship as less than or equal to y I x I minus 1, and this can be shown is nothing but equal to 0. So, what I get is finally xi log of 1 by xi I is equal to 1 to q is less than or equal to xi log of 1 by yi I is equal to 1 to q. So, this relationship we will be using it later on in our course. So, it is a very important relationship which we get when xi and yi are two sets of probabilities. So, this inequality will be equal only if xi is equal to yi, because we have seen that these two equations are equal only for x is equal to 1. So, correspondingly, if you want equality out here, what I should get is yi is equal to xi, and from there I get this relationship. So, we have seen that entropy of the source is given by this expression. Let us try to find out what is the maximum value, if it exists, for what probability distribution function of Si will I get the maximum value for Hs. Let us try to find out that. This we will try to do it for a zero memory source. So, if I have a zero memory source, that source will be identified S given by source alphabet. I will assume the source alphabet is S1, S2 and SQ are the symbols of the source alphabet. Along with that, I will get the probabilities for the symbols, or sometime the symbols in the source alphabet are also known as letters. So, the probability associated with the letters of the alphabet are also given to me, and I assume that the source S is a zero memory source. Let us, I will try to simplify this. PSI, I will write it as P1, P2 up to PQ. So, my entropy for the source Hs is nothing but Pi log of 1 by Pi, I is equal to 1 to Q. let us try to evaluate this expression log q minus h of s. I can write this very simply as pi log q I equal to 1 to q minus pi log of 1 by pi. Since pi are the probabilities, summation of pi's is equal to 1. So, for log q I can write this expression. This I can simplify as pi log of q pi, and as a simplification, instead of writing every time I is equal to 1 to q, I can say that the summation over is the source alphabet. So, I just write the source s. This implies that I am summing up I from 1 to q, that is denoting the alphabet. Okay. So, this I can simplify as log of now at this instant I can use the previously derived inequality which is given by graphically log 1 by x is always greater than or equal to 1 minus x. So, I can use this relationship to write as greater than or equal to and this you can show very easily is nothing but equal to 0. So, from this I get the relationship as log of q is greater than or equal to h of s. A very important relationship which we have derived. The first important relationship which we have derived in information theory is this. This both are equal only when I look at the point where the inequality was introduced. It was at this instant of the time. So, if you want the thing to be equal, what it should happen is 1 should be equal to 1 by q pi. This implies that pi should be equal to q for all i's. If I can satisfy pi is equal to q for all i's, then I can write log q is equal to hs. So, what it means that entropy hs is always less than or equal to log q, and it will take the maximum value of log q when all pi's is equal to 1 by q. Sorry, it is not pi is not q, but 1 by q. So, what it means that all the symbols or the letters in the alphabet occur in a equiparable fashion. Okay. Let us take a simple example of a binary source. I have a binary source which is 0 memory. So, if I have a binary source, let me denote the alphabet for this binary source S as 0 and 1. Let me also associate the probabilities with this letters of this source as probability of 0 is equal to w and probability of 1 is equal to 1 minus w is equal to w bar. If I assume that this binary source is a 0 memory source, then I can write the entropy for this binary source as hs is equal to Now, in the information theory literature, you will find that the expression on the right hand side, this is a function of W and it occurs very frequently. So, if I denote this as a function of W, then I write HW as W log 1 by W plus. If I write like this, then HW is basically termed as entropy function. It is important to realize the difference between these two expressions. This is an expression for the entropy of a zero memory binary source, whereas this is an expression for an entropy function, which, like any other function, is the variable is W out here, whereas here for given W, this is the entropy function, entropy which I will get for a binary source. Let us look at the property of this entropy function. If we plot the entropy function HW versus W, you will get something like this. This is my HW and this is my W 0 1. What it shows is that when W is equal to 0, HW becomes 0, and when W is equal to 1, HW again becomes 0, but when W is equal to 0.5, my HW becomes the maximum value, and that is equal to 1. So, for a zero memory binary source, if I have probability of 0 and probability of 1 both equiprobable equal to 0.5, then the entropy of that zero memory binary source would be nothing but equal to 1 bit. So, this is the maximum entropy I have of a zero memory binary source. We know that if we have binary source, then physically if I want to assign some symbols to those two symbols, okay. Let us look at some of the physical implications of entropy. Let me take a simple example. Suppose I have a graphical grid which is 4 by 4 given like this. And I number them from 1 to 16. And let us say that one of this grid is marked. I mark this grid. My problem is to find out, ask questions and find out which grid has been marked. My answers will be only in terms of yes and no. So, I can make a guess and ask someone, is the grid number 7 marked? The answer which I expect should be in terms of yes or no. The answer I will get obviously is no. So, if I use this kind of procedure to find out which grid is marked, the worst case I can ask from 16 questions. I can say whether grid number 1 is marked or not marked, and I expect the answers. So, in this case, if I go in a serial fashion, at the 10th question I will get my answer. So, I will require 10 questions to be asked before I get the answer which grid is marked. Is it possible for us to find out what are the minimum number of questions which you should ask, whose answers we expect in terms of yes and no, in such a way I can find out which grid is marked. So, in this case what I can do, a clever way of finding out which grid is marked, I can ask a question saying which of the, I can ask a question simply like this: is the marked grid lies in the bottom 8 grid. So, what I am saying is that the marked grid, whether it lies on the upper side or the lower side of this line. So, obviously the answer I would get is yes. So, I have asked the question once whether the grid lies on the top or the bottom. Once I get that answer, I know the grid, that marked grid lies somewhere from 9 to 16. Now, the next question which I can ask is the marked grid lying on the left of the remaining 8 regions? The answer would again be yes. So, I know that it is between 9, 10, 13, 14, either one of this. Again I can ask a next question is my grid lying on the top or the bottom? This case he will say it is lying on the top. So, if I say if I ask the question is lying on top, the answer would be yes. So, I get a third answer yes. Now, finally I would ask the question, is the grid lying on the left? The answer would be say no. So, I know the grid is basically 10. So, I required 4 questions to be asked before I could find out which grid was actually marked in this graphical picture. Is it possible for me to relate this minimum number of questions to the concept of entropy which we have just seen? If you look at this from the information theory point of view, I can say that the probability of marking any grid would be 1 by 16, because I have 16 values out here, and any grid can be marked randomly or equiprobable. Then I can find out what is the entropy associated with this grid, and what I will get is summation of pi log 1 by pi I is equal to 1 to 4, and in this case it will turn out to be nothing but 4 bits. Always the logarithm is to the base 2. Right? So, what it means that, and since we are asking in terms, the answers we are expecting is in terms of zeros and 1, what I get here entropy also in terms of 4 bits. This gives a relationship between a mathematical concept and the physical experiment which we have carried out to find out which one of the grid is marked. So, this is an simple application of information theory. We could have many more applications. In this course, we will restrict our application to only communication systems. Now, the way we have defined entropy here was for a single source S emitting single symbols SIs. The question that comes to my mind is it possible assume that if I have a source S and if it emits symbol Si, instead of considering this symbol Si individually, if I start blocking these symbols in some length, let me assume in the length of 2, that means what I do is that when I have S1, S2, Si, Si plus 1, I start blocking them in terms of 2, so I get like this. Now, if I start blocking in terms of like this, then what I can assume is that I am forming a new source whose symbols are coming out in group of 2, but each of the symbol in that group of 2 is coming from the primary source S. If I start interpreting the output of this source S in terms of another source which I have written here like this, then is it possible for me to relate the entropy of this new source to the entropy of my primary source? Is there some kind of a relationship? And if there is a relationship existing, what is the usefulness of such relationship? We will look into this matter in the next lecture.